So we are trying to use this operational amplifier to explain what we have. Okay. We have the operational amplifier that has a gain of up to 320,000. And then it is connected up here as a feedback amplifier. So you will see that the non-inverting input here has the input voltage connected to it. And then the output terminal is wired back through resistor R1 to the inverting input. And so we have a feedback network there. You see the signal here showing the feedback network. You also see that there's another resistor that is connected from that same terminal, inverting terminal, to the ground. That is a feedback voltage, VF. Then we have VA here. We have VA. Now, the open loop gain of the amplifier is 320,000, and the output voltage is taken from the output terminal here. Now, the closed loop gain G, which we use the notation A prime, not G, A prime. The closed loop gain A prime equals V out divided by V in here, and that is 1 plus R1 over R2. 1 plus R1 over R2. That is the gain of the amplifier after negative feedback. Now, beta, which is the feedback fraction, equals VF divided by V out. VF divided by V out, and that is R2 divided by R1 plus R2. R2 divided by R1 plus R2. If you look at this amplifier, it is still like the initial one that we have up there, but it's like they turn it the upper part to the lower part now. Here we have the minus part up here, and we have the positive part down. But they turn it around. The example that we have here, we now have the minus part down, for the up, we have the positive terminal up, but it still remains the way we connected it up there. The input voltage is connected through the non-inverting terminal, and the feedback is connected to the inverting terminal. So let us see one example now. Let us use this example to exemplify what we are trying to pass across here, so that we see how to use the formula that we have there. I want to see how to use the formula that we have there now. Okay. Okay. We have this formula given here. We have two expressions, the beta and then the gain after feedback. So let us see how we can calculate that using this example. The example is this: an operational amplifier with an open loop voltage gain AVOL of 320,000 without feedback is to be used as a non-inverting amplifier. Calculate the values of the feedback resistance R1 and R2 required to stabilize the circuit with a closed loop gain of 20. Closed loop gain of 20. So we are given only two parameters. The first one is the open loop gain, 320,000. That is AVOL. The closed loop gain is 20. All right. If you use our previous notation, this 320,000 is the A prime. 320,000 is the A prime. 320,000 is A. The 320,000 here is A. Whereas this 20A, closed loop gain, is A prime. 20A is A prime, closed loop gain. Now let's look at it. The generalized closed loop gain that we have been using is given as A prime equals A divided by 1 plus beta A. And then when we rearrange this formula, we can rearrange it so that we can get beta in this format. Look at the way we rearrange, making beta the subject of formula. A prime multiplied by 1 plus beta A is equal to A. To cross multiply. Then 1 plus beta A is equal to A over A prime. Then beta A is equal to A over A prime minus 1. Then therefore, beta is equal to 1 over A prime minus 1 over A. That's it. So if you now use these two, the values given, the values of A prime and that of A, they are given in the example, you can get beta out. Beta is equal to 1 over A prime minus 1 over A. That gives us beta equals 1 over 20 minus 1 over 320,000. The answer is 0.05. So our beta is 0.05. All right. Now, because in this case, the open loop gain is very high, we have 320,000. The feedback fraction beta will be roughly equal to the reciprocal of the closed loop gain. That is 1 over G, or what we call 1 over A. 1 over A prime. So beta is roughly equal to 1 over A prime. Okay. Because 1 over A is very, very small. 1 over A is very, very small. So the beta now, which is the feedback fraction, is equal to 1 over 20, which is 2.05. So if you look at it, 1 over 20 is what takes precedence. 1 over 320,000 is negligible. So the answer is beta equals 1 over 20 because the open loop gain A is very high. Open loop gain A is very high. All right. So when you look at the question now, we are told to calculate the value of resistor R1 and R2. Now we have determined only one value, that is beta. For resistor R1 and R2, none of them is given. But we know that they form a series voltage potential divider around the operational amplifier. So we could now determine them, as follows, using the ratio that we have. Beta is equal to VF over V out. Beta equals VF over V out, which is equal to R2 divided by R1 plus R2. Beta equals R2 divided by R1 plus R2. Now, we will assume one of these values to determine the other one. It's like a practical work that you are designing a feedback system using the operational amplifier. So we could now choose a value for one of the resistors and now calculate what will be the value of the second one. Now, if we assume resistor R2 has a value of 1000 ohm, that is 1 kilo ohm, then the value of resistor R1 can be calculated from this formula here. That is, if you choose a value first for R2, then we can determine R1 from this equation you are looking at. So we could have R1 equals R2 minus beta R2 divided by beta. That is if you make R1 the subject of the formula. To make R1 the subject of formula, we have that. That is 1000 minus 0.05 times 1000 divided by 0.05. That is about 19,000 or 19 kilo ohm. 19 kilo ohm. Now, the beautiful thing here is that if you are designing such a system, and then two people who are designing, individual of them can assume their value for resistor R2 differently. And for that reason, they are going to get different values for resistor R1. So it means if you give it to a class of 20 students, you could actually get 20 answers here because it's a design. You are choosing your own first resistor yourself and calculating the second. But everybody must follow the same procedure. Everybody must follow the same procedure. So for the non-inverting amplifier circuits, to have a closed loop gain of 20, the value of the negative feedback resistors required will be R1 19 kilo ohm and R2 1 kilo ohm. And that gives us the inverting amplifier circuit like this. Look at the screen now. We now have the inverting amplifier like this. K is equal to 20. Okay. We have the closed loop gain is equal to 20. The resistor R1 is equal to 19 kilo ohm. Resistor R2 is equal to 1 kilo ohm. So the gain of the amplifier has been reduced from a value of 320,000 to 20, but with very high stability added to the circuit. So the major advantage that we have here is that before we have very high open loop gain, but now we have very small open loop gain, but with a lot of stability. We have greatly improved stability, and then it has better tolerance to component variations. The circuit has a better tolerance to component variations, and it stabilizes against DC drifts, as well as increasing the amplifier bandwidth. We have mentioned all these points previously. Those are the advantages of negative feedback on an amplifier. So it stabilizes against DC drifts, is it's having high tolerance to component variations such as component variation due to temperature rise, and then it's having an increased amplifier bandwidth, increased amplifier bandwidth. Now, we have examples of negative feedback in common amplifier circuits where we have resistor RF, and then in the circuits like we have above, and then resistor RS in the feed effect transistors. You use a feed effect transistor as your amplifier, and then resistor RE in bipolar junction transistors. So we have a typical example of that. So that is how we use operational amplifiers as a feedback system, as a negative feedback system. It's very simple and straightforward. So I think we can stop here for today. We can now entertain your questions. Now you can raise your hand if you want to ask a question. You can raise your hand if you want to ask a question.